Uh, so yeah, so I guess I'm going to wait for 5 minutes for people to join. Hello, everybody. This is our second live interaction and doubt clearing session, and I am Shresht Gupta, as I've already told you. And here is the detail. This is assignment number 2. It will be having 10 questions based on week 2 classes, and similarly the time is 3 p.m. to 5 p.m. Yeah, the date is different. Sorry for the mistake. Yeah, 3rd Feb 2024. So I'm waiting for 3-4 minutes for some people to join, and if they do not join, then I'll start. Hello there, Arumugam Ramanji.
Hello.
Yeah,
Good evening, sir. Good afternoon. Good afternoon, sir.
good afternoon, good afternoon. So where
How are you?
I'm good, I'm good. Where are you from?
I'm right now in Nigeria, sir. I'm basically Tamil Nadu.
Okay,
I'm right now working in Nigeria.
so
I'm working in healthcare sector, healthcare.
you are a postdoc or a PhD, or you're working in a healthcare department basically.
I'm working in healthcare sector department, sir. I'm working now.
So
So I want to upgrade my nuclear medicine technologist. I'm right now radiography,
okay,
CT scan, MRI technician.
okay, wonderful.
So yes, sir. So I have a good scope of nuclear medicine. That's why I'm trying to attend this course. So I'm last 2 days before only I know this course about it. I joined that one.
No, I mean actually it is not my course. Actually, I am a TA. I am myself a
Oh,
PhD scholar, so I just come here for clearing out the assignment questions, and like
okay, okay,
there is a assignment every week on your website. Also,
okay.
I have a YouTube channel too. So
Yes, sir. I last night, yeah, last night only I watched it, sir. That one.
last week
I
video.
don't know about it. Yeah, last week video I noted. I seen it, sir.
Okay, great, great. So we will start at around 3:05.
Very wonderful your explanation, everything.
Okay.
Mm. Today is nobody's come yet.
So we will wait for one more minutes, then we can start. So have you gone through the week 2 classes?
Okay.
No, have you gone through the week 2 classes? Have you seen the week 2 classes?
No, sir. I finished only 1 week classes. Second week I know completely, sir.
No, no. You have seen week 1 classes or week 2 classes? Because week 3 are also from this Friday will be present. Have you seen week 2 classes?
Okay.
Or I can give a quick recap of what is being taught in the week 2 classes.
Week two classes I seen only the first 6 day lecturer only, sir.
I mean,
Six week, six lecturer only I see.
no, no, that thing, that
7, 8 months.
liquid drop model, shell model, all that you have seen the video of Professor Tomar.
No, 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 sir. Not
Okay,
yet,
okay,
sir.
no problem. So it's
I will,
3:05.
I, I will start. I will start today onwards.
No
Because
problem.
of this course, I am joined 2 days before only. So
Okay.
I seen the first week, 3 days only the last time.
So
Huh?
okay, just for you and also for the other viewers, I'll give a quick recap,
Okay.
quick recap of
Okay, sir.
what is being taught now and what is like. So
Okay, sir. Okay, sir.
what happens, we know very well what is radioactivity. It is a process in which certain nuclei of certain elements spontaneously disintegrate. I have already shared this PDF. This is a short note, and
Okay.
I've already explained this in my
Okay, sir.
last video. But just for a quick recap, I'm going to give starting 15 minutes. Uh,
Okay, sir.
what I have done, this is short note. Along with that, I
Mm.
have combined all the PDF of week 2 classes. So I'll give a quick recap of
Okay, sir.
what Professor
Okay,
Tomer has taught, so that at least whatever
okay, sir.
assignment I'll be discussing, you will be able to understand. So without delaying,
Okay, sir.
could
Okay, sir.
could
Okay,
you
sir.
mute your mic? It will be really helpful. So if you have any question,
No
please.
problem, sir. I will meet, sir. I will meet, sir.
Yeah,
First, I look at the your presentation, sir. Then any question I will ask you, sir.
yeah, definitely. So yeah,
Thank you, sir. Thank you, sir.
so talking about radioactivity, as we have already gone through the previous week, this is for those who have not joined and who will be lately seeing in the YouTube channel. So we know this is a process of in which nuclei of certain element spontaneously disintegrate at a rate characteristic of each particular active isotope. So this could be alpha emission, beta emission, and we know what happens in alpha emission and beta emission. I hope that there is a change of atomic number, there is a change of atomic mass, and then there are isotopes, isobars, isotones, isodiphers, isoelectronic elements, and isostars. And I hope that we all know it very well. So there is a law of radioactive disintegration. This is from week 1 classes, all the short notes. We already know what is the law of group displacement law. The result of alpha beta particle changes can be summed in a group displacement law. What happens that in an alpha particle change, the resulting element has an atomic weight less by 4 units and atomic number less by 2 units, and it falls in the group of a periodic table with two columns to the left of the original element. And in a beta particle change, the resulting element has same atomic weight, but its atomic number is increased by 1. Example, PO is there. When this is happening, atomic number changes by 2 and this changes by 4 atomic mass. So this is alpha emission. So what is happening from polonium to Pb, when we are moving, it is changing the group. This is called as group displacement law. And then all this thing we have already been through, the half life, average life, specific activity, how do we calculate. It's just for a week 1 quick revision. What is activity, what is decay constant, what is half life. All these things I think we have already seen, and these are some useful hints. So I have shared this PDF with already in the Google Drive, so you can go through it. Now coming to the week 2 class, sir. So this was a week 2 class in which Professor Tomer has started with a nuclear stability. So in the first class he has explained what is nuclear stability. So what happens, he has talked about elements with magic numbers. So what happens when we have even mass number, even atomic number, and n is also even, they are stable isotopes, and there are 165 stable isotopes till now. But when there is something odd in the atomic number or capital N, then there is what you know there is a change, which is not a stable isotope. So elements with Z equal to 20, 50, 82 have more number of stable isotopes, thus they have extra stability with magic numbers. This is how Professor Thomas started, and then he explained what is N by Z ratio and how does it actually control the nuclear stability. So there is this plot, so you can go through the lecture, and if you have any problem you can write me down. Then what is nuclear force? So what holds the proton and neutron tightly inside a nucleus? It is a nuclear force, and it is short range and attractive. We have to remember the properties. Neutron and protons behave similarly with regard to nuclear force, and they are together called as nucleons. And neutron and protons are half spin particles. Remember it, they are fermions. So electron, proton, and neutron are the elementary particles of matter, but there are certain more particles which we are not aware of. Now, when we read just the chemistry, we just know that there are three elementary particles: electron, proton, and neutron. Now, going to deeper nuclear chemistry, Yukawa in 1935 talked about mesons. So what happens when a proton and neutron combines? It can give birth to certain particles which are called as mesons, which could be pi plus meson, pi minus mesons, or pi dot meson. So pi meson survives for 10 raised to the power minus 24 second. You see, and the range of nuclear force is around 10 raised to the power minus 15 meter. It's very short, and the mass of pi meson, just a minute, the mass of pi meson is 140 mega electron volt. And does it not going to violate the law of conservation of like Heisenberg uncertainty principle. So Professor Tomar has explained it in his first class. Then there are certain characteristic of nuclear forces. It is charge independent, it is spin dependent, it has short order, and it is saturated. So please go through them. Then there are certain properties: nuclear spin, magnetic moment, quadrupole moment, statistic, and parity. Parity, what is parity? Now comes the strange particles. What are strange particles? Or we talk about the cosmic rays or in accelerators. So what happens? Different particles can be grouped into two classes. One class is hadrons and the other class is leptons. Hadrons are what? They're strong interacting particles which can be baryons or mesons. And leptons are weakly interacting particles: electron, tauon, mu, all these particles. So depending on the integral spin, whether they have the half integral spin or integral spin, and they are weakly interacting or strongly interacting, they can be further distributed as baryons, mesons, etc. So please go through them. So are the proton and neutron not the elementary particles? This is a question that remains still. So to answer it, there comes the concept of quarks. So there, what are quarks? So just go through the video for detailed discussion, and if you have any problem, write me in the email. I'm just giving a quick recap so that before I go to the assignment solving, you just remember what has been taught in the week 2 class, as it becomes very difficult for me to match the frequency. So Gelman and Zizek give the flavor and color. So just to see, there are certain flavor which is UDCSTB. U means up, D means down, C means charm, S means strange, T means top, and B means bottom. So there is a Q by E law. Q by E is plus 2 by 3 for U, C, and T, and Q by E is minus 1 by 3 for D, S, and B. So for what happens for a proton? For a proton, it is UUD. That means Q, if we calculate the quark for this, Q is equals to plus 2 by 3, that means U, plus 2 by 3 U, and D is minus 1 by 3. U plus 2 by 3, U plus 2 by 3, and D is minus 1 by 3. That's why proton has a positive charge. And for neutron, the quark comes as 0 by Q by E law. Therefore, it is neutral in nature. Okay. Wonderful. Now comes the concept of leptons. Leptons are light particles, are not made of quarks. They participate in the electromagnetic weak interactions, but not in strong interaction. Remember it, they do not participate in the strong interactions. And if we calculate the QIE for them, if we call it these particles, electrons or neutrinos, all these particles, the QIE is minus 1, and for these particles QIE is 0. So these all are leptons because they are light. Masses of leptons are much less than those of quarks with MEC square. That means multiplication of their mass with the speed of light is around 0.511 mega electron volt. So for different particles it is the multiplication with the speed of light. So neutrinos are very much lighter than their rest mass and may even be 0. Okay, so this is the speed which is there because of them being lighter. So leptons, these are the particles which are involved in the beta decay and other weak transitions. So what is happening, there is a bound proton and neutron, how this neutrino is coming outside, and whether this will combine or not combine, what is the time scale in which all this is happening. It was explained in detail. Please see the video. This was the first class of week 2. Then comes the second class of week 2 where he has talked about various nuclear models. First is the liquid drop model and second is a shell model. Liquid drop model deals with the gross properties. So yeah, and shell model deals with the fluctuations. So what happens, there is empirical shell corrections to LDM and there are many body calculations, and for nuclear reaction there is optical model. So going to the liquid drop model, which was given by Niels Bohr, liquid drop model says what? Nucleus is like a droplet of incompressible matter and all nuclei have same density. Nuclear force is short range and attractive and operates between nearest neighbors. Nuclear force is saturated like van der Waals force between the molecules, and the binding energy can be termed as a heat of vaporization of a liquid drop. So if we consider the nucleus to be a liquid drop, these are the characteristics which a liquid drop model tells us about. So there are certain semi-empirical formula masses, like what happens if we calculate the mz by a. So this is where A is a mass number, Z is atomic number, and N is a neutron number, we calculate the binding energy. Now the binding energy can be the sum of volume energy, surface energy, Coulomb energy, asymmetry energy, and pairing energy. Now what are these energies and how these come into the picture? Let's see. So what happens? There is semi-empirical formula mass. Volume energy is directly proportional to the volume, and VV represents VE of infinite nuclear matter. Now surface energy is the nucleons at the surface that miss the attraction from the outer side. Now surface energy is directly proportional to the surface area, and Coulomb energy is due to the Coulombic repulsion between protons, and these are the formula: volume energy, surface energy, and Coulomb energy. And then other two energies are we can say yeah, asymmetry energy and pairing energy. Although I will upload this PDF also in my drive, in case you are not able to search it on a website, it is already available there. You have the videos there. I'll share this PDF also where in detail everything is written, and then I'll discuss the assignment also, which will help you. So yeah, asymmetry energy, this is fraction of volume occupied by X-ray neutrons, and then we calculate. And then there is a pairing energy, for which we have del equal to 0 for odd A nuclei, negative for odd nuclei, and positive for even nuclei. We need to remember it. All these are we say the characteristics of liquid drop model, and then we calculate the liquid drop model energy. Formulation comes like this, and then there are certain characteristics. So this is the characteristic representation of average nuclear binding energy, which is term of volume, surface, Coulomb, asymmetry, etc. So this is a graphical representation. Now moving forward, there are certain application of LDM. What happens? It can predict the atomic masses and binding energy. Okay, you can predict the atomic mass and binding energy by using liquid drop model. And then in the next lecture, in the third lecture of week 2, he told about the application further, which is the energetics of beta decay. How do we calculate the energy? And then all these parameters, some mathematics is there, and then mass parabola for constant. All this you need to go in detail in the video only. Then how this QB in odd A isobaric chain happens. So yeah, please go through the video, and all this is very greatly explained. The most important thing is this thing. Please remember the graph and the markings. What are these dots corresponding to, and what happens in an even A isobaric chain? Now there is a problem exercise. For example, there is this PM, and then this is giving ND and PR. So the Q beta positive, if we say, it is 3.72 mega electron volt for ND and 1.82 mega electron volt for PR. So we have to calculate the Z naught, for which is the most stable isobar. So we use the formula this. We put the values. 2 gamma 61 minus Z naught, 61 is PM, minus 0.5 equal to 3.72. From here we calculate the gamma and then Z naught, and then we calculate what will be the Z naught, which that will be the stable. So it will stop till here. It does not stop here, it will go till here. Why will it go through here? It is being explained by liquid drop model. I cannot cover it in this short term, but yeah, this just giving a quick recap. We can calculate the energy release in a nuclear fission also by this model, and yeah, we can see these two gets cut off when we are calculating the energy. Remember it, because this will be a question in the assignment when I will discuss. So these two terms get cancelled out. Remember what are these two terms, and only these terms correspond when we are calculating the energy of fission for uranium, zinc, or moly. Okay, so then there is spontaneous fission. Liquid drop model explains spontaneous fission as due to the competition between surface energy and Coulomb energy of the nucleus as a function of deformation. Remember, spontaneous fission is the competition between surface energy and Coulomb energy. No other energy comes into the picture. Neither like you say some other energies were there. No, among these 5 energy, only 2 energies are there which correspond to the fission process when it is spontaneous. Okay, so moving forward, in last second lecture he told about the limitations of liquid drop model. So what are the limitations? Extra stability associated with magic number of protons and neutrons. The magic number is there, no, 2, 8, 20, 50, 80 to 80, 126. Why are they extra stable? The liquid drop model cannot explain it. Very high separation energy of neutrons and protons for nuclei having atomic number or n equal to 50, 82 or 126. Very low separation energy or neutron proton for nuclei having one nucleon excess over these magic number, and very low neutron absorption cross section for nuclei having n equal to 50, 80 to 126. In simple, these all are the magic number properties. And then largest number of stable isotopes, and beta delayed neutron emission, and existence of nuclear isomers. So all these things that exist, liquid drop model was not able to explain. Then there comes into the picture shell model. So what does a shell model assume? The shell model was given by Mayer and Jensen in 1949. We just got independent at the time, just 2 years before, and they were doing nuclear chemistry. So what they assumed in the shell model, nucleons move inside the nucleus under the attractive potential. There is a potential which is there inside, which is attractive in nature, which are generated by the remaining nucleons. So neutron and proton move in separate potential wells. Now there comes a quantum into the picture. If you consider it as a potential well, then neutron and protons are moving in a separate potential well, and nuclear force is assumed as weak as the nucleons in different orbit do not interact. So Pauli exclusion principle is followed. So you can go into these notes in detail. So this is the plot, and then considering a harmonic oscillator potential, he calculated the n nuclear number, which is n equal to 2n minus 1 plus L. So from here shell model states the harmonic oscillator potential, and then from here they calculate that why this magic number is there and why does not reproduce. Now there comes the concept of spin orbit coupling, because there were certain magic number which were not able to explain by the only shell model, and then spin orbit coupling, ground fitting, and then all these three number which were not being explained by only shell model. There we have to consider this splitting. These terms also come into the picture because these splits. So how do they split? They have explained in the shell model, and then there is a last lecture in the week 2 in which he has explained the application of shell model. So which explains the mass number, high spins of the magic nuclei, and then low neutron absorption cross section, ground state spin and parity of nuclei, and nuclear isomers, magnetic dipole movement and electric quadrupole movement of nuclei. I know it is a lot of information in one go, but I need to give a quick recap before discussing the assignment. Then this shell model has very well explained the magic numbers, and then there is a ground state spin and parity of nuclei. What is parity? This is same as a parity operator in quantum, which makes a negative into positive and positive into negative. So how this parity, which is a reflection symmetry, comes into the picture, and how does it control the ground state spin, and how does this parity actually control the shell model stability. So there are certain discrepancies in the shell model prediction as observed, pairing energy effect, collective model, etc. are there. So please go through them, and if you have any kind of question, then come back to me. Then there comes the term of nuclear isomers. So those which have the change that is delta L same, they are called as nuclear isomers. So you can go through them. There are certain example, and then that's it. So basically we give a quick recap. I know you must not have understood a lot if you have not gone through the videos, but if we give a quick recap, what we have studied till now, we have studied what is radioactivity, how this alpha beta gamma emission takes place, and what are the theories that explain them, which is the most strongest radiation and their properties, and how do we calculate certain numerical based on them. Then there came the concept of binding energy, what is holding neutron and proton inside, and then comes the concept of strange particles that except neutron and proton there are many particles, mesons, hadrons, leptons, fermions, which are existing. So what are they? And then comes the concept of why this fission actually happens, why certain atomic number particles are more stable. To explain it, some theories came into the picture. One theory was a liquid drop model, and the other theory was shell model. and then Sir has given some quantum dependent calculations using the Schrodinger equation, and then the potential come into the picture, and then at last, using shell model, the concept of magic number was proved and explained, taking into account the splitting of the orbitals. So ground state spin, all these things you have to go through. I cannot teach them in such a small time, because it is around 5 hours and 5 hours 10 hours lecture till to week 2. So I've just given a quick recap. So are you there, Mr. Arumugam?
Hello? Yes, sir. I'm here. I'm Yes, I'm online.
Okay, so
Yes, sir.
now I'm going to start the assignment. So
Okay, sir.
hello, I'm Shresh
Hello.
Gupta.
Yes.
Yeah, now you can mute. I'm going to explain. So
Okay.
I'm
Okay.
Shresh Gupta, and I have already given access to you, everybody, to my drive, and there is a YouTube channel where this video will be uploaded, and these are the questions based on the assignment of week 2. Also, along with that, I have made some question of myself. Still, after that, when you go through the video, if you have any query, please write on this email to me. My email is sg19ib011@isacol.ac.in, and I am a Prime Minister Fellow at IISER Kolkata, and I work on material chemistry. And so moving forward, so Arumugam ji, the first question is saying there is a radioactive nucleus which emits 3 alpha particles and 2 positrons. For the resultant nucleus, the ratio of neutron to proton, they are asking the ratio of neutron to proton. So what will be the ratio of neutron to protons for the resultant, where the initial nucleus to the atomic number is Z and atomic mass is A? Can you solve this question, Arumugam ji?
Yes, sir.
Will you be able to solve this question?
Sir, this is first time I am attending this one. I know watch the video.
Okay,
I
okay,
no idea this one, sir.
no problem. I'll explain.
Yes, sir.
Now I'll go
Yes.
slowly.
Okay.
I have just given you a recap
No
of
problem, sir.
what has been explained till now. Please go through the videos.
Okay.
But yeah, I have given the
Okay,
solution
sir.
in
Okay,
detail.
sir.
Yeah. So the
Okay, sir. Okay. Thank you, sir.
answer is this. So what happens, Arumugam ji? For every alpha particle emission, the mass number is decreases by 4. Okay, and number of proton decreases by 2. Everybody knows it. When there is alpha emission, when there is alpha emission occurring, just a minute. So what happened when there is an alpha emission occurring? As already explained, there is a change in atomic number and there is a change in mass number by 2 and 4, and positron is beta positive. Okay, so now they are saying that there is a 3 radioactive nucleus which emits 3 alpha particle and 2 positrons. So what will happen? For alpha particle emission, mass number decreases by 4 and number of proton decreases by 2, and for every positron emission, proton number decreases by 1. Remember this. So number of neutron will be the mass number minus the number of protons. How? Because mass number is what, Arumugamdi? What is mass number? Do you know? In a nucleus, you have protons plus neutrons. Okay, this is the mass number, the sum of
Okay.
protons and neutrons. So suppose you know how many protons are there, right? So
Yes, sir.
by subtracting number of protons from the mass number, you can get the number of neutrons, right? Do you understand?
Yes, sir.
Okay,
Yes, sir.
okay. So seeing here, for every alpha particle, there is this mass number decreases by 4, and proton for positron, proton number decreases by 1, and we know number of neutron can be calculated by mass number minus number of proton. Now suppose initial neutron number by a minus z. Now number of protons are z minus 8. Okay, so the number of
Okay, sir.
a minus z, why it is a minus z? Z is what? Z is what? Atomic number.
Mass atomic number.
Yeah, and atomic number is what? Atomic number is the number of electron or proton, right? So
Okay.
suppose in an initial state when there was no emission of 3 alpha particle and 2 positron, the initial neutron number must have been a minus z. Suppose the mass number is a
Okay.
and number of proton will be equal to the atomic number, so the initial neutron number will be a minus z. Now
Okay, sir.
number of protons will be how many? There is 3 alpha emission and 2 positron emission. Okay, so for 3 alpha emission,
Okay.
there will be a disturbance of how much protons. For 1 alpha emission, the proton decreases by 2. So for 3 alpha emission, the proton will decrease by how much? Tell me. Okay, so what is happening? There is 3 alpha emission and there is 2
Just wait.
positron.
Yeah.
So in a alpha emission, if there are 3 alpha emission happening, so for 1 alpha emission there is a change of atomic number by 2. So for 3 alpha emission there will be a change of atomic number by what? Tell me. Arumugam ji.
Hello, sir.
Yeah, for 1 alpha emission there is a change of atomic number by 2. So for 3 alpha emission
Okay.
there will be a change in atomic number by how much?
Like 6, sir.
Yeah, very good. It will be by 6. Great.
Okay.
So now there is 3 alpha emission and then there is 2 positrons, right?
Okay.
So for one positron,
Okay, sir.
there is a proton number decreases by 1. So for 2 positron it will decrease by how much? For one positron
It's like
there is decrease by 1. So for 2 positron there will be a decrease by how much?
0.
No, for one positron if it is decreasing 1, for 2 will be 2. Why it will be 0?
And this one I no idea, sir.
Okay, wait, let me explain it. So there are 3 alpha
Okay.
emissions
3.
and
Okay.
2 positron emission. Okay, so
Okay.
about 3 alpha emission we calculated that there is a change in atomic number by 6, right? Now
Okay,
for
sir. Yeah, yes, sir.
2 positron emission there is a change in atomic number by 2. So
Okay.
the total change in atomic number will be what? Can you tell me?
Odd it's a 8, sir.
Yeah, good. This will be 8. So
Okay, sir.
what happens? The number of
Okay, sir.
the total number of protons will be z minus 8 and the number of neutron will be what? A minus z. That means a minus 12 minus z minus 8. Okay.
Okay, sir.
So now if we calculate the ratio of number of neutron to number of proton, this will be a minus z minus 4 over z minus 8. Are you able to understand the answer?
I half understand, sir. I half confusion, sir. I will.
Okay,
Yes,
so
sir. This is my first time lecturer. That's why I'm half only. I understand your lecturer.
yeah,
I didn't see the Dr. Professor Thomas sir lecturer, so I didn't
okay,
see.
so it's okay. You remember only one thing: when there is an alpha emission, there is a decrease of 4 in mass number and decrease of 2
Mm.
in atomic number. And for positron, there is a decrease of 1 in atomic number. Now there are 3 alpha
Okay.
particles which are getting emitted, and they are asking the ratio of neutrons to the protons. The final number of protons will be as 3 alpha has been emitted and 2 positron have been emitted, so there is a change of
Okay.
8 protons. So the final number of proton are z minus 8. Okay.
Okay.
Now the mass number is what? Mass number is number of neutrons plus number of protons. Right?
Okay.
So if we calculate the number of protons, they are asking the ratio of neutron to the protons. So the
Protons.
number of neutrons will be mass number. So what is the total mass number? So for every alpha emission, there is a change in mass number by 4. So for 3 alpha emission, there
Mm,
will be a change by 12. A minus 12,
okay.
this is a mass number, and number of neutron will be mass number minus number of protons. Z minus 8, how does it came? I told you, right?
Yes, sir.
Yeah. So the mass number, number of neutrons will be mass number, which is a minus 12, minus number of protons, which is z minus 8. This is a minus z minus 4. So this is the final number of
Okay.
neutron that we have. This is the final number of
Okay.
this is the final number of neutron, and this is the final number of protons. Okay.
Proton.
Yeah.
Okay, sir.
Now they are asking us what is the ratio of neutron to proton. This is the question that this is asking. So just put them in a fraction. So by putting them in a fraction, ratio of number of neutron to proton is a minus z minus 4 over z minus a. So what is the option? The correct option is option number 1. Okay.
Okay, sir.
Please go through it once again. Still, if you have problem, please write to me. Okay.
Okay, sir. I will write the
And
mail, sir.
these 3 4 questions are from the week 1 classes, by the way. Till here, till question number 2, these are from week 1 classes only. I just wanted to discuss if people remember it or not. Okay. So the question number 2 is saying the half life of a radioactive substance is 10 years and its initial mass is 1 gram. The remaining amount after 20 years will be what? Okay, so I know you have not gone through it. I'm just showing you. So they have given us the half life. Okay, the half life is 10 years. Initial mass is 1 gram.
Okay.
Initial mass is 1
One.
gram, and they are giving the time 20 years, and they are asking the remaining amount. So what happens? Half life is what? Half life. I have tried to make the assignment in detail as much as I can, and still if you cannot understand, you have to go through the notes because I cannot teach the complete class. Okay, so what is half
No
life?
problem. No problem, sir.
What is half life, Arumugamji? Arumugamji, half life is a time period after which half of the quantity. So what happens?
Okay.
It is a time period in which half of the quantity of the radioactive elements gets decayed. That means only half remains. Suppose you have 1 gram.
Okay, sir.
So after the half life,
Half means.
half means the half amount. Zero point 0.5 will be remaining.
Okay. Half a month.
Yeah, half amount. So the fraction of substance, if you have, suppose if you have n naught initially, the
Mm,
after one half life, it will be n naught by 2. Okay.
okay. Okay,
Now,
sir.
if I say after 3 half life, what will be the fraction? Then it will be n naught by 2 raised to n, which will be,
Me and. Okay. Then when I will send it. Are you the one doing next week? Yes. Both up here. Let him be sending, oh. It's supposed to be submitting. Alright, take a deep breath. Relaxing also be accessing. Yes. Okay. Relaxing also accessing.
okay. So Arumugamji has gone. I am explaining for others. So we know the half life. What is a half life? So after n half life, it will be n equal to n naught by 2 raised to power n, where small n is the number of half lives. So small n, which is the total number of half life, is the total time. Just a minute. Okay. So small n is a number of half lives. So from here, if we calculate small n, it is total time over half life. That gives us a number of half life. Suppose there is 1 gram, 1 gram change into 1 gram change into 0.5 gram, and 0.5 gram change into 0.25 gram. That means 2 half life have gone. So this small n is the number of half lives. Now, what is the question saying for us? The question is saying for us that the half life of radioactive substance is 10 years and initial mass is 1 gram. So we know if initially it was 1 gram, in 10 years it will become 0.5. I mean, there is no point of even writing it. It is a very simple question. You see, you have 1 gram initially, Arumugamji. Okay, now there is a half life. After one half life, it will become 0.5 grams, and after another half life, it will become 0.25 grams, and after another one half life, it will become 0.125 gram, and it goes on. So these are, this is n equal to 1, and this is n equal to 2, and then this is n equal to 3. So suppose if I ask the 1 gram initial compound after 3 half lives will be the final amount of what? It will be 0.125 gram. So suppose the half life is, suppose if I say, suppose the half life is 10 years. So after 10 year, after 10 year, it will become 1 gram will change into 0.5 gram. Okay, and after another 10 years, this 0.5 gram will change into how much? 0.25 gram. So this is a basic concept that you have to remember. Now look here, what are they saying? That they are asking the remaining amount after 20 years. So we put the value, that number of half lives we will calculate. So 10 years means one half life, 20 years means two half life. So in one half life 1 gram will become 0.5 gram, and then another half life 0.5 gram will become 0.25 gram. So the right answer is fourth. The correct option is option number 4, which is 0.25 gram. Are you there, Arumugam ji? Okay, no problem. He is not there, I guess. Now question number 3 is saying which of the following pairs has two magic number for closed nuclear shells? And the answer is from the class where sir has explained nuclear stability from frequency distribution of stable isotopes, and he has shown that how many stable isotopes are there. Majority of the stable isotopes has even J and even N. Only 4 OO nucleons like to be remained paired. Okay, elements with Z equal to 20, 50, 82 have more number of stable isotopes, extra stability with magic number 2, 8, 20, 50, 82 and 126. So which one of the following pairs have the two magic number of for closer nuclear shells? The correct answer is option number 3, that is C, 50 and 82. Okay, the question number 4 is saying, it is from the assignment number 2. The question is saying which of the following statements are correct? Nuclear force is short range, nuclear force is attractive, nuclear force is charge dependent, and nuclear force is spin dependent. Just a minute, let me give a quick recheck that whether my video is getting recording or not. Yes, it is getting recorded. So this is also from Professor Tomer class. He has explained in his class very well certain properties of nuclear force. Nuclear force, it is charge independent. EO stable, OE stable, it is same. Okay. NP, PP, NP interaction does not matter. It is neutral, it is positive, it is charge independent. Nuclear force is charge independent. It is spin dependent. Okay, where if the spin is opposite, it is unstable, it is in same direction, it is stable. Okay, it has short range and it is saturated. So B by A, this is the average nuclear binding energy. It is constant if each nucleon interacted with all other nucleons. So B by A is directly proportional to the A. So the correct option is D. Nuclear spin is spin independent. No, nuclear spin is spin dependent. So the next question is quark structure of neutron can be written as. The answer is like this: quarks. Quarks can be divided as flavor and color, red, green, and blue. Okay, flavor can be UDC, STV. U is up, D is down, C is charm, S is strange, T is top, and B is bottom. There are 6 kinds of flavors of quarks. We know these 6 kinds of flavors: QI equal to plus 2 by 3, UCT, and QI equal to minus 1 by 3 for D, S, and B. U is up, D is down, C is charm, S is strange, T is top, and B is bottom. For proton, it is U by D. So for proton, it is UUD. For UUD, I mean, we have to follow a combination where it should come plus 1. So the only combination is UUD. Up, up, down. Okay. Plus 2 by 3 plus 2 by 3 minus 1 by 3, it gives plus 1. For neutron, it is neutral, that is UDD. Q equal to plus 2 by 3 minus 1 by 3 minus 1 by 3, which is 0. So the quark structure of neutron can be written as what? The quark structure of a neutron can be written as UDD. I'm sorry, the correct option is 4. I have written is wrong. UDD, which is 4. I thought if there would be somebody in the discussion, he will point me out, but as nobody is there, so I myself has corrected myself. This is 2. Yeah. Okay, moving to the next question. Question number 6. It is saying average binding energy of a nuclei is nearly constant, which suggests that the nuclear force is what? Short range, spin dependent, saturated, and attractive. The B by A, it's nearly constant because it is very short range. If it will be very long range, then it will violate the Heisenberg uncertainty principle. Please go through the lecture. Week 2, lecture number 7 and 8 has detailed talked about this, and these are the classes where Professor Tomer had actually talked about these things. Okay, going to the question number 7. Liquid drop model explain fission in terms of competition between what? Is it a competition between asymmetry energy and Coulomb energy? Is it a competition between surface energy and asymmetry energy? Is it a competition between Coulomb energy and surface energy? Or is it a competition between Coulomb energy and pairing energy? Are you there, Mr. Arumugam? Are you there, Mr. Arumugam? Okay, no problem. Going here, liquid drop model explains fission in terms of competition between Coulomb energy and surface energy. We have actually explained this in the application of liquid drop model 3, class number 8, 8th and 9th, class number 8th and 9th of week 2, where he has calculated the Q value using liquid drop model, where he has also plotted the plot between B by A versus A, which is the average binding energy. So considering a symmetric fission and neglecting the pairing energy, the equation becomes QF equal to mz comma A minus 2 mz by 2 comma A by 2 equal to 2b z by 2 comma A by 2 minus bz comma A. Now these two terms gets cancelled out, and finally it comes as a combination of Coulomb energy and surface energy. So this is a competition of Coulomb energy and surface energy. Example for uranium 238, QF comes as minus 130 plus 300, which is 170 mega electron volt. For 64 zinc, QF comes as minus 4.97 mega electron volt, and for 100 molybdenum, the QF comes as 10.36 mega electron volt. So please go through the lecture. Still, if you have some problem, I will be more than happy to clear it out. The question number 8 is saying select the properties of nuclei which liquid drop model cannot explain but shell model can explain. And the options are nuclear masses, ground state spin, nuclear isomers, or energetics of beta decay. As there is nobody in the audience to interact with me in this live interaction, So I will tell the answer myself and wait at last for if some people will join, and if not, then it's okay. So select the properties of which nuclei which liquid drop model cannot explain but shell model can explain. It will be nuclear masses or ground state spin or nuclear isomers or energetics of beta decay. The answer lies here. Limitations of liquid drop model, which is lecture number 9. It cannot explain what? It cannot explain the extra stability associated with the magic number of proton and neutrons, which is 2, 8, 20, 50, 82 and 126. Very high separation energy of neutron proton for nuclei having Z or N equal to 50, 82 and 126. A very low separation energy of neutron proton for nuclei having one nucleon excess over these magic numbers. Very low neutron absorption cross sections for nuclei having N equal to 50, 82, 126. Sharp drop in the alpha energy for each alpha emitter isotope having N 126. Largest number of stable isotopes, beta delayed neutron emission, and existence of nuclear isomers. So the liquid drop model cannot explain what? What it cannot explain, the ground state spin. Okay, so before going to the question number 9 and 10, let's see this. Classify each nuclide as stable or radioactive. 30P15, 98TC43, 10118 and 239Pu94. Given they have been given mass number and atomic number, asked for the predicted nuclear stability. The strategy is what? We have to use the number of proton to neutron to proton ratio and the presence of even or odd numbers of neutron and proton to predict the stability or radioactivity of each nuclide. Solution is like this. You can see the isotope of phosphorus has 15 neutrons and 15 protons, giving neutron to proton ratio of nearly 1. Although the atomic number is 15, which is much less than the value of 83 above which all nuclei are unstable, the neutron to proton ratio is less than the expected for stability of an element with the mass as shown in the figure. So its neutron to proton ratio must be greater than 1. Moreover, this isotope has an odd number of both neutron and proton, which also tends to make a nuclide unstable. Constantly 30P15 is predicted to be radioactive, and it is radioactive in nature. Talking about Tc, which is technetium 9843, it has number of neutron as 55 and photons at 43, which gives a neutron to proton ratio of 1.28, which places Tc 9843 near the edge of the band of stability. The atomic number 55 is much less than the value of 83, above which all isotopes are unstable. These facts suggest that technetium 4398 might be stable. However, technetium 9843 has an odd number of both neutron and protons, and a combination of that seldom gives a stable nucleus. Thus, it is predicted to be radioactive, and it is radioactive in nature. Now, let's talk about tin 118. SN 118 has 68 neutron and 50 protons for a neutron to proton ratio of 1.36 as in part V. This value and atomic number both suggest stability. In addition, the isotope has an even number of both neutrons and protons, which tends to increase nuclear stability. Most important, the nucleus has 50 protons, and 50 is one of the magic number associated with specially stable nuclei. Thus, 50 SN118 should be particularly stable. Last is saying Pu, 239 Pu94. So this nuclide has an atomic number of 94. Because all nuclei with Z greater than 83 are unstable, that is why 239 Pu94 must be radioactive in nature. So this is how we predict the stability of a nuclide, whether it will be stable in nature or radioactive in nature. Okay, now going to the question number 9 and question number 10. Question number 9 is saying which is the heaviest stable nucleus having the magic number of protons and neutrons: 204 lead, 206 lead, 208 lead or 209 lead. Heaviest stable nucleus, I have already explained you how do we calculate the stability of a nuclei. So you need to calculate using the same concept, and the correct answer is 208 PB82. It is less than 83, so you have to calculate the number of protons and neutrons and then the ratio, and then see which amongst them has the highest ratio, which is the most stable. Now The first four shell model states in increasing order of energy R. This is 1s 1 by 2, 1p 3 by 2, 1p 1 by 2, 1d 5 by 2. How the splitting is happening, it is well explained in lecture number 10 of Professor Tomer, which is here, I guess. Yeah, just a minute. There it is. That how this pairing energy affects, and what is the collective model. So as the shell model also, without considering the splitting of the spin and parity of the nuclei, was not able to explain the stability of the magic number of 50, 82 and 126, and also the concept of nuclear isomers. So for explaining these concepts, we have to take into account the splitting of the spins, and also the ground state and parity of the nuclei. Okay, so the right answer is 1s 1 by 2, 1p 3 by 2 and 1p 1 by 2 and 1d 5 by 2. That is all for the class, for today's class. If you have any query, please feel free to write me. And I am again sharing my YouTube channel for you people for help. This is my YouTube channel. I am writing in the chat. If you somehow miss the class, you can go through. This will be uploaded here, and also my drive is there, whose link is already been shared. You can access all these notes and solve assignment from the drive. So I'll wait for 10 minutes more. If somebody joins, then it's good. If nobody joins, then I'll close the recording and I'll leave. So I'll wait for 10 minutes here. If somebody joins, please come and speak.
Hello, I'm sorry, sir. I'm here to your presentation, but I'm inside the procedure room. Hello, Kutta sir.
Yes, yes.
Hello,
Just a minute.
hello, hello, Gupta sir.
Yeah,
Are
yeah,
you audible my voice?
yeah. I can hear you voice. You cannot hear me. Just a minute. I'm reloading.
Are you audible?
Yeah, am I audible?
Yes, sir. Yes, sir. Yes, sir. I am
Okay.
in the procedure room. I went. I put your percentage in everything. I hear it.
Hmm.
So that's why I moved to the volume.
Okay.
Sorry,
It's okay.
but
So
I everything I heard it. Your Bluetooth, everything.
so that is good. You have the recording. This will be
Mm.
uploaded in my YouTube channel. And
Okay,
also,
sir. Okay, sir.
I think I have given you access to the drive also, where the solution will be uploaded. So please go through the
Okay,
videos,
sir.
and
Yes.
if you have any
I
problem,
will,
please let me know.
I will watch it, sir. I will watch it. And
Please let
another
me know.
also, I recommend my two colleagues. Next week will join, sir. Nigerians. He
Okay.
also physicist and chemistry.
Oh,
Will
wonderful.
join your lecture, sir.
Wonderful.
Yes,
Wonderful.
we already registered this week about the course. We
Okay.
complete this week. We will make next week classes. He will come, sir.
Okay.
Two guys, my colleague.
I just want to ask you, Arumugam sir, what do you do in
Mm,
Nigeria?
yes, sir.
Like you are into this medicine stuff. So what
Uh,
do you?
uh,
Hmm.
I do exactly now use radiology, NASA radiology field, CT scan, MRI, X-ray,
Okay.
special procedure, nuclear medicine.
Hmm. So in
Um,
nuclear medicine, like what kind of medication do you give?
we do FTG, sir, for
Oh,
fluoro deoxyglucose. We injecting the PET CT
oh, wonderful.
and gamma also. Yes, sir. That's why I want to upgrade my skill. That's why I'm joining this course,
No,
sir.
no, then this course will be really good for you. I will suggest you to at least go through week one, week two, and in the next Saturday, I will be explaining on the
Mm,
level of week three classes. So you should go through all these 15 lectures. You can put
no problem, sir.
you can put it on 2x. You can put the lectures on
Yes, sir. Yes.
2x or 3x,
Yes.
and you can even skip a
Okay.
little bit if you have somewhat of knowledge. No, it will be good for you. And
I'm basically BSc radiology, sir. My education.
wonderful.
BSc radiography. Yeah, that is most of only the physics only the have radio physics, X-ray physics,
Hmm.
CT scan physics, MRI physics only.
Hmm.
But this one is full and full is a chemistry.
Hmm.
That's why when I was in the higher secondary plus one plus two,
Hmm.
that's why I'm trying to understand. Then this course about it I know only 2 days ago. Then
Hmm.
only I register, I join, watch the video, everything.
Okay.
I don't know before it. My colleague's nuclear technician also is refer me in India.
Hmm.
Then only I see the NPTEL. Then I register, I follow. Then my colleagues also I told them. He also very interested.
Hmm.
And join maybe next week will live classes will come.
Okay. Okay.
My colleagues only. Yes sir. Yes sir.
Okay. Wonderful. So then I'll put the recording on YouTube, and then next week, let's see at the same time today.
Yes, I last night watch your YouTube channel, sir. I check
Okay.
everything in that website.
Okay.
I that's why I last night I watch your everything. I
Hmm.
I I whatever my friend I tell your YouTube channel, sir.
Yeah, YouTube channel, and
Subscribe
also
and watch it.
and also ask them to see the NPTEL videos of Professor Tomar.
Okay, sir.
Okay, and also ask
Any
them.
of my questions, I will send you your
No,
email, sir. No
yeah,
problem. You
one.
have WhatsApp number, sir?
Yeah, I have WhatsApp number. I can write it to you.
Yeah, please, sir.
Yeah, yeah. You have to add Indian code.
Okay, sir. 755, huh?
Hmm.
Disappear that one. Where is good, I see. Only 9 1 only I see, sir. Where I foresee.
Oh, you didn't see?
Sir.
The number is this. Just a minute. I'm just sending it to you. Now you can see
7375
3861.
3861.
Yeah.
Okay, sir. I will add it Indian code. No problem, sir.
Okay. Okay then. See you in the next
Thank you,
week.
sir. Your wonderful presentation. But I'm working now, right now, X-ray, the special procedure. That's why
Okay.
I enter the room, process room.
No problem.
But I hear your presentation, everything. Very good.
Okay.
But next week I try to some solving the questions.
Okay.
But I have watched this video, everything.
Okay. Wonderful. Okay then, Ananji.
Okay, sir.
Okay.
Thank you, sir. Thank you, wonderful, sir. Thank you, sir.
See you. See you in the next week.
Okay, sir. Thank you, sir. Thanks, sir. Nice to your lecture.